Welcome back. Our next chapter, we will be talking about work and energy. For this section of the notes, we're going to cover Roman numerals 1 and 2. So we're going to talk in depth about work and then touch a little bit on the concept of power. So let's get started. As you can see, the definition for work is the product of the applied force times the displacement in the direction of the force. Now, you've had all of these concepts before. We've talked about applied force and we've talked about displacement, and hopefully you'll see that the direction is really important. So that means that work is going to be a vector quantity. So I'm going to go ahead and draw in the vector notation in our equation. So work is going to be force times displacement, and all three of those things are vector quantities. Now, when we look at the units, force is measured in newtons, displacement is in meters, and when we multiply those two together, we get a joule, which is abbreviated with a capital J. You probably saw that in chemistry when you talked about energy. And speaking of energy, one of the definitions that you might see for work would be the transfer of energy by mechanical means, and we're going to come back and touch on that a little bit later. There are several different things that work can be done against, and so I'm just going to list these for you and go through a couple of definitions. If you do need to stop and pause the video, feel free to do that if you want to write down some extra information. The first thing that work can be done against is gravity and other fields. And a definition, or an example for this would be if you were to lift an object, then you've done work against gravity. Now, when we say other fields, that means electric or magnetic fields, but that's something that we'll talk about right at the end of the year. So for right now, we'll just talk about gravity. The second thing that work can be done against is inertia. In order for work to be done against inertia, it requires that the object must accelerate. So remember, we've applied a force, and now if that object accelerates, then we've done work against inertia. For the third thing, elastic substances, an example of this would be if you stretched out a rubber band or a spring or something like that. And then lastly, you can do work against friction. So if you were to, say, bump a book, the book would keep going forever if there were no friction. But since there is, you have to continually apply work to keep it moving. So think about Newton's laws and how those might apply to these scenarios. We can also reclaim some of the work against these different categories. Now, when we say that work is reclaimable against, it simply means that work is done in the opposite direction of what we applied in the first place. Again, I'm going to go kind of quickly, so feel free to pause the video and write down any extra information that you want. What I'll actually test you on will be the amounts of work that you can get back, and then I'll reveal some examples. So if we were to lift an object, we have done work against gravity, and it's possible to get all of that work back, which means the object would return to its original position. For inertia, we can also get all of the work back if we did something to accelerate an object. That work that we put into an object could be used for some other purpose. Now, for elastic substances, you notice that the amount changes from all to most or some. That's because most elastic substances are going to lose their elasticity over time. So we can't quite get everything back that we put into it. And then lastly, with friction, this is the bad one. You cannot get anything back from friction. So if I were to push something forward and slide it along a table and let go, there's no way that that object's going to return back to me in any way. So friction eats up all of your work. Remember at the beginning that we talked about how work is a vector quantity, so the direction of the force is going to be really important. Work is done only if the force is exerted in the direction of motion, and if we have a force exerted at some angle, then we're going to use our components. So remember sine, cosine, and tangent when we had a right triangle and we were given the hypotenuse. When we looked at those x and y legs, that's what I mean by components. So if a force is exerted at an angle to the direction of motion, it's only the component in the direction of motion that contributes to the work. And so we'll talk about an equation for that. So in your copy of the notes, you should have a picture of a little wagon. So think about when we pull a wagon, we would be applying a force along the direction of the handle up this way. Well, the actual displacement of the object is horizontal. Those are at an angle to each other. So what we're going to do is break down our force into components. So what I did was I took that little triangle from the handle and I turned it into a bigger triangle that we can see a little bit more clearly. So the hypotenuse would be the actual force that we apply, and we make an angle right here of whatever degrees you might choose. And then when we turn that into a right triangle, we're breaking it down into an x and a y component. Now, is it the x leg or the y leg that's in the same direction as the actual movement of our object? Hopefully you recognize that that's in the x direction. So what that means is it's our x component that actually contributes to doing the work. So I'm going to make some substitutions. If we look at that formula that we had at the beginning, force times displacement, it's the x component of the force that's contributing to our motion. So I'm just going to substitute in fx and specify that it's just that part of the force. And then I'm going to use cosine, and I'm going to substitute in and solve for the f of x right here and plug that in. And what this gives us is another version of the work formula. Typically, you'll see the order written as the one in the box right here. Work is force times displacement times the cosine of the angle. And you can still put in those vector notations if that helps you to remember. So whenever you're given a word problem and you see an angle at all, you're going to use this formula when the force and the displacement are not in the exact same direction. So we're going to pause and do some example problems. We're going to lift a 3 kilogram object from the ground straight up to a height of 1.5 meters. I hope you recognize that you've done work against gravity at this point. So we're going to look at our formula as being work is force times displacement. We're lifting straight up. So the force that we are applying is in the same direction as the actual movement of the object or its displacement. So I can simply plug in. But wait, hopefully you recognize that force is measured in newtons, but we were given kilograms. I hope you remember from last semester how to convert mass to weight, because that force that we have to apply would be lifting the weight of the object. So let's stop and do that first. And to get an object's weight from its mass, we simply multiply mass times gravity. And notice that I wrote out the word weight because weight is a capital W and so is work, and I didn't want you to get confused. So now we figured out our force is 29.4 newtons, and we can simply substitute into the work formula. And when we type that in, you should get a work of 44.1, and then remember the units are joules. Now for our second example, let's go through and identify all the variables for the numbers that are given. So we have a force of 25 newtons. The handle of a lawnmower is at an angle of 40 degrees to the horizontal. And you should know when you push a lawnmower, we're actually going to be moving along the horizontal. So this will be the angle that we use. And then it tells you that 190 joules of work is done. And we are asked to find how far. So we're looking for the distance. Since we are given an angle, we're going to use the version of the work formula that is force times displacement times the cosine of the angle. And you can simply plug in your numbers. So you plug those in and see what you get. A couple of things you want to be really careful about is make sure your calculator is in degree mode. And if you're not too great at parentheses, because remember we can divide by the 25 and the cosine of 40, remember that you'll want to include parentheses around that entire denominator if you do this in one step. Regardless of how you typed in your numbers, you should get a value for that distance of about 9.9, and distance is measured in meters. For our next example, we're just going to talk about a scenario. So let's say that I am going to lift this box. Are you doing work when you lift something? Hopefully you said yes, and the answer is because you're doing work against gravity. I'm applying a force upward, and the box is moving upward, so I've done work. Since there is no angle between the force and the displacement, they're in the same direction, I could mathematically say that the cosine of 0 plugged into that FD cosine theta formula, this particular part would give me an answer of 1, so it would simply reduce down to force times displacement, because there's 0 degrees between the force and the displacement when I lift something. For this next part, I'm going to go over this again in class, but I want you to have a little bit of an introduction to it. If I were to carry an object, think about carrying something. You have to actually apply a force in the upward direction because you're preventing that object from falling as you carry it. But our displacement is this way as we moved across to set that object on the table. What's the angle between those two? Hopefully you said 90 degrees. So if I were to plug into my formula, work is FD times the cosine of the angle. If my angle is 90 degrees and you type that in your calculator, the cosine of 90 is actually 0. So there is no work done anytime you carry an object. Again, we're going to talk about this a little bit more in class. I just want you to have an introduction. Now let's say we lift the book. Is work done? Yes. We carry the book across up high over our head. Is there any work done? No. 0 work. And I set it back down. Oh, remember it's a vector. So if positive was up, negative work was down. So overall, remember that the displacement is what matters, not just the distance. So I began in this position. I ended in this position. In both cases, they had the same displacement. So that means the same amount of work was done. And again, we'll go over this again in class so you can actually see an example physically in front of you when we talk about these. And again, we're going to do this example in class of somebody climbing a mountain, but remember that work is a vector quantity. It's the displacement that's important. So go ahead and write this sentence down, that work is independent of the path taken. It only matters where you start and finish because it's displacement, not distance, that matters when we talk about work. Next, we're going to look at a force versus displacement graph and relate that to the work that we've been talking about. So you're given a graph in your notes. How far did the crate move horizontally? So we want to look for the displacement. It started at 0 and it moved all the way over here to 0.5. Next, what was the magnitude of the force? So we look at where the force was applied and where it crosses that y-axis. And that magnitude of the force would be 30 newtons. Next, we're asked what the area under the graph represents. Well, if we have a displacement and we have a force, what have we done with those so far? We've multiplied them. So if I look at the area of a graph and I dropped a line straight down and I looked at this little shaded section right here, if I found the area of that rectangle, I would be multiplying force times displacement. And I hope you recognize that when you multiply these two things together, this gives us the work. So if you're ever given a force displacement graph, finding the area is how you would calculate the work because you're simply multiplying length times width, which would be force times displacement. The last concept for this section of the notes is going to be power. It's very short. Power is simply the rate of doing work. And remember, whenever you see that word rate, that means we're going to divide by time. So that simply gives us a formula of power, which is a capital P, is the rate, so we're dividing by time, of doing work, which is a capital W. Unit-wise, you should see a watt on typical light bulbs. This is where that comes from. We've got joules for our work, and that rate is per second. Whenever you see a joule per second, that is what determines a watt, which is also a capital W. So I'm going to make you a little note over to the side so that you don't get confused, or at least to give you something to look out for. Unfortunately, we see these in the same chapter, but a capital W can be work, weight, or watts. So it's going to be really important that you pay attention to the context when you're reading those word problems, and we're going to get some practice with those. The other thing that I wanted to make a note of for you is that watts are pretty tiny, so a lot of times you'll see a kilowatt, so you may need to do that conversion from watts to kilowatts. So there are 1,000 watts in 1 kilowatt. And then also for our work up here, you could substitute FD or FD cosine theta into the equation to simplify that down and use other variables. So I've got a couple of practice problems for you, and we'll see how you do. And I know this is typically about the time that we end our videos. However, we're going to do a lab where you're actually going upstairs in class. So we're going to use the staircases at the front of the building. You'll need to know how to solve this problem in order to do your lab. So let's do this one together. Let's say we have a 45 kilogram woman, so we know her mass, and she's going up a staircase that's 4 meters high. That's going to be our distance or our displacement, and it takes her 5 seconds. So you should recognize that that would be a time. And we are asked to find her power. Well, power is going to be work over time. So remember, that's work, not weight. And to find the work, typically we do force times displacement. But we're given a mass instead of a force. Do you remember from the other example problem how we got force if we knew a mass? Well, we're lifting an object, so we want to turn that into weight. So I wrote you a little note. We're going to do that. We're going to turn the mass into weight, and that's going to be our force. So to do that, we're simply going to multiply mass times gravity. And this gives us 441 newtons for the woman's weight, which we will be using as our force. Now that we know that, we can either find the work first and then plug it into here, or you could substitute in force times displacement and then divide by the time for the power. I'm going to break it down into steps and say that the work is force times displacement, and in this case our distance and displacement are the same thing because she only moves in one direction. So we're going to multiply the weight of the woman, which is a force of 441 newtons, times the 4 meters that she climbs up the steps. And this would give us a value for the work of 1,764 joules. So that gives us part of our answer, but remember we're interested in the power, and power is work over time. Now that we've found the work, we can simply make that substitution and divide by our 5 seconds. And this gives us a power of 352.8. And if you remember, the unit for power is watts. All of these steps in this example problem is something you'll need to do in your lab, so make sure that you go back and watch this again if you're having trouble, or that you ask me about it before we do that activity in class. For these next 2 examples, I'm going to get you set up with them, and then I'd like for you to pause the video, plug in the numbers, and see how you do. So these were the variables that you should have identified, matching up the numbers to which variable. Our 2 formulas are going to be work is FD cosine theta, and power is work over time. You can do this in 2 parts, find the work first and then substitute in, or you can go ahead and make that substitution first, and then your formula would become power is FD cosine theta, which is the work over time. It's up to you. So either way, try this out and we'll see what you get. Whether you substituted early or did this in 2 steps like I did, you should come up with an answer of about 9.4 watts. We've got one more example problem to try and then we'll be done. Ooh, this is a challenge problem. I'm going to identify the variables for you and then show you what to do. For this one, we're going to do a few mathematical substitutions and see what we can come up with. Remember that power, because we know we definitely have power, is work over time. There's no angle mentioned at all. We're assuming that the boat's going to travel in the same direction as the force that's applied to make it move. So that would be force times displacement over time, and that's equal to our power. Look. Ooh. Displacement over time look familiar? Way back at the beginning of the year, displacement over time is the same thing as velocity. So there's a little bit of manipulation on our formula to come up with a velocity because we were given that of 4.5 meters per second. Now we can substitute in and it should be really easy for you to find the force. So go ahead and do that and check your answer. Hopefully you got somewhere in the neighborhood of 14,000. So I did both scientific notation and wrote out the number for you. Good luck, and we will practice some more in class. I do apologize, this was longer than usual, but we had to get through power in order for you to do our first activity when we come back next week.